So, good evening, and my name is Isaac Opio, and I'll be presenting about the prediction of energy and nutrient composition in poultry feed formulation using the planning. A very good evening once again. So, basically, we're going to engage in the project, or the idea here is, a multi-output regression approach for feed formulation what optimization. So basically, you find that feed formulation plays a critical role in ensuring poultry growth, health, and productivity. The challenge lies in currently what predicting nutrient composition. For example, the Me, the CP, the lysine, the methanoyl C and P avail based on complex ingredient interactions. So back then, there have been methods that have been employed. I can call them traditional, like the linear regression, but they fail to capture nonlinear relationships. Because a linear relationship is one that is, you know, more direct and easy to come up with, or easy to what to streamline. But here we are looking at, what if a farmer has, a variety of ingredients? They want to be able to predict outcome of the ingredient composition from a variety of mixtures of feeds. Now there we go into what nonlinear relationships and more complex. So basically, when we look at the problem statement, you find that traditional methods do not account for non-what linear interactions between ingredients, leading to suboptimal what formulation. So the objective here is to develop a deep learning model to be able to predict and be able to tell, multiple nutrient values simultaneously to improve the formulation accuracy, to improve, the works of the feed poultry what farmers. The dataset description. Now, the dataset consists mainly of feed formulations, and it is in various categories of broiler, starter, broiler finisher, layer chicks. These are different, poultry stages. So the datasets we have been having can be more of broken down into various classes, and developing models for each of the what? Each of the data sets. So when we look at the input features, those are just proportions of ingredients such as maize, soya beans, fish meal, basing on what metrics you're using to what? To blend them, to mix them. Then the target outputs will be the energy that will come out. What amount of energy? What is the proportion of energy that comes out from the what? From the mixture that you've made up. What is the crude protein, the CP, crude protein? When you see CP, we're talking about crude protein. On CME, we're talking about metabolizable energy. So we are looking at a farmer mixes, various proportions of ingredients or nutrients, and wants to be able to predict what is the output of, the amount of energy that would come up with from this what from this mixture. What is the amount of output that would come up from this other, when I mix this other proportion of values, this and this, what could be the output? That is basically the model. So we look at the methodology. We're going to venture into data collection. We are basing on historical data on feed formulations and nutrient outcomes. Then data pre-processing, data cleaning, of course, takes place. And in our data set, we had to realize there were some cells within the data set that, or there were some formulations within the data sets that did not have certain ingredients. But basically, to neutralize and, standardize the whole data set, we had to replace them with zero values. Then there were, data sets that, had the same value for certain ingredients. The proportion did not change. Then model development, we're looking at, shall be having a multi-layer what perception for multi-output regression. Then model training, we shall be having a hyperparameter tuning, shall be training and also do some validation. That's now the methodology we're going to be employing. Then the evaluation will be based on metrics such as R squared, MAE, and LSM, RMSE. Looking at the architecture of our model, it will be broken down into about four divisions: the input layer, hidden layers, the output layer, and the training. That's the architecture we're going to be employing. So The input layer is comprised of 21 input features. Those are 21. Those are the ingredients. When you look at the data set, it's going to be having 21 ingredients. Then the hidden layers, those will be, the training layers that, you know, the layers with which the model is going to be training. So when you look at the output layer, we shall be basing on six outputs: the metabolizable energy, the crude protein, that is MECP, lysine, then methionine, CA, and PAVL. Then we look at now the training. We shall employ the Adam optimizer and the mean squared error for loss functioning. Then looking at the results, the model was trained over 100 epochs, only that you can adjust accordingly based on the kind of accuracy you want to receive. Then we were able to come up with a table that explains the actual versus the predicted what values for a test sample. As you can see here, the actual value. Let's look at for example, the metabolizable energy. The actual value was actually 3,000, but the predicted was 3,550. When you look at the crude protein, the actual value actually in the table was 22.1, but when you look at the one that was predicted, it was 26.3. So there's a small variation there, but definitely the model will need more training and trying to to tune it into better accuracy. So the visualization of the training, we're able to see from our graphs that when you look at as we keep increasing the efforts in the initial training, you find that the training loss and the validation loss is really very high. But as you know, the efforts keep increasing, it all stretches down to try to reduce the training loss and the validation loss. And also when you look at the scatter plot we had where the actual against the predicted of the nutrient values, you realize that the model actually is trying to learn because it managed to categorize, the actual values together with the predicted what nutrient composition, whereby you find those color codes represent different outputs. And basically, in conclusion, the deep learning model successfully captures the nonlinear relationship between the feed ingredients and model outcomes. And we expect to expand the dataset in the near future and explore new architectures and define predictions. I believe this is the end of my presentation, and here are some of the references from part of the information that is in our write up. These are the references that I managed to what to record.